Today we will review the paper ZeroNVS, Zero Shot 360-degree View Synthesis from a Single Image by Stanford University and Google Research. The model creates 360 novel views of real-world scenes from a single image. It combines a 2D diffusion model with a 3D distillation step, called score distillation sampling, and a viewer-centric camera representation, achieving state-of-the-art results without scene-specific fine-tuning. And let's begin. This work tries to tackle some limitations from previous NVS work. First, limited and usually object-centric datasets. There's not enough real-world 3D scene datasets, and most large-scale datasets, and therefore most research, focus on single objects. The second limitation is camera parameterization. The problem here is that existing representations are too simplistic and cannot meet the requirement when generating real scenes. The third limitation is about lack of background diversity. Score distillation sampling used in NVS tends to produce monotonic background, especially when it's not observed in the input. To address the limitations, ZeroNVS builds solutions in a two-stage pipeline. Stage 1 is to train a 2D conditional diffusion model to learn to predict novel 2D view conditioned on an input image and target camera parameters. It is trained with a mixture of different datasets to handle diverse indoor, outdoor, and object-centric scenes. This, of course, makes the second limitation even worse, because now we have more diverse camera settings used in different datasets. A full 6 degree of freedom extrinsics plus a field of view representation are used as camera parameters. The authors then propose a viewer-centric normalization to handle scale ambiguity. In stage 2, score distillation sampling is applied, using the guidance of the trained 2D diffusion model to optimize the 3D representation, in this case a neural radiance field. Now, to solve the mode collapse commonly observed in SDS, authors propose SDS anchoring to first generate a few diverse anchor novel views using DDIM sampling before distillation. Let's look at stage 1, the 2D conditional diffusion model. This stage is a standard diffusion model training similar to prior work, such as 0123. It is trained with a mixture of CO3D, RealState 10K, and ACID datasets. A key technical contribution of ZeroNVS is its camera conditioning scheme that handles arbitrary real-world scenes. Previous methods use 3 degrees of freedom, only capture camera elevation, azimuth, and radius, creating this various distance dome shape pointing inwards. ZeroNVS uses 6 degrees of freedom, including 3D rotation and 3D translation, allowing it to model the free movement of camera in a scene properly. It also uses camera field of view to be able to do mixed training on different datasets. To handle the scale ambiguity, the translation parameters are further scaled by a depth-based scale factor, Q. Here, Q is defined to be the 20th quantile of the densified depth map of the input view. This is noted as viewer-centric normalization in the paper. It ensures that scenes with very different scales are normalized to a similar one. Stage 2 is 3D distillation via score distillation sampling. SDS is proposed in the Dream Fusion paper. It distills 2D diffusion model into NeRF by optimizing a 3D representation to match 2D guidance from the diffusion model. Here SDS uses the gradient of the diffusion model to guide parameter optimization in NeRF. The standard SDS, however, is prone to mode collapse, especially in background regions that the single input view doesn't observe, usually ends up with bland, uniform backgrounds. This is addressed by SDS anchoring. First, the 2D diffusion model is used with DDIM sampling to create multiple anchor novel views around the input scene. This step leverages the inherent diversity of the 2D diffusion model, which is less prone to mode collapse than SDS. Next, during SDS optimization for a particular viewpoint, ZeroNVS picks the closest anchor view as guidance. Instead of always conditioning on the single input image, the model can effectively use the anchor that's most similar in pose for this viewpoint. This ensures that each region of 3D space is guided by a diverse anchor image, leading to more realistic and diverse results. One thing to be aware of is that in the supplementary material of the paper, the authors mentioned that such method can sometimes lead to artifacts because there's no 3D consistency guaranteed from the generated anchor images. And in practice, they only do this for regions with a depth more than 1 meters, only impacting the backgrounds. Now let's look at the evaluation and results. ZeroNVS achieves state-of-the-art LPIPS even compared to methods fine-tuned on DTU dataset. They also propose to use MIPNERV 360 as a harder single-image 360-degree benchmark. ZeroNVS again performs strongly on LPIPS, which is the metric more aligned with human perception than PSNR or SESIM. From the ablation study, we can also see that the training on mixture of dataset, as well as proposed camera conditioning, improve the result. Lastly, the user preference study shows that SDS anchoring is better than standard SDS, both in realism and creativity. To conclude, ZeroNVS has achieved strong zero-shot performance, robust scale handling, and high background diversity. The core innovations include the better camera conditioning by 6 degrees of freedom, plus field of view representation, and the viewer-centric normalization, and the SDS anchoring to help with background diversity. In my opinion, this paper can be considered as a direct extension over the prior work, 0123. We can see the zero-shot generalization ability coming from prior knowledge obtained from training on extensive mixture of datasets. It also brings up the question of how do we infuse model with 3D consistency in the novel view synthesis tasks. That's it for today. Until next paper, thank you.